So now we get into bonding, chemical bonding. Okay, so let's do this. So there are very few elements in this world that exist by themselves, which means that a lot of them are found in combination with something else. So they combine, they bond, and sometimes it's hard to kind of remove them, kind of separate them, I should say. So even something as simple as oxygen is actually found as diatomic. It's not found as elemental O, it's found as diatomic, as O2. So in this chapter, we are really going to learn about what bonding is, okay, and how it works, what we do, all those kind of things, okay. So a lot of things to learn in this chapter. So let's get started. So first we need to understand is why bonding occurs, okay? So bonding generally makes something more stable. So what is considered to be more stable? Anything that is stable means it's not going to react. So taking a lesson from noble gases, we try to understand why noble gases don't react with anything. And it turns out that noble gases don't react with anything is because their valence shell is full. It's full of 8 electrons. If you look at the electronic configuration on the periodic table, okay, or your periodic table, if you look at that, you will see that you start filling lithium, you'll go all the way to neon, and then you will turn around and start filling sodium with the next shell, go to argon, go to the next shell. So which means at any given time, you have maximum of 8 electrons in the valence shell, okay? So which means 8 is the maximum you can have, because after that the electrons start going into the core, right? So it means that the rule of 8 is what is important here, and that is called the octet rule, which means that any element or ion that has 8 electrons in its valence shell is going to be stable, which means that every element strives to have 8 electrons in the valence shell. How it gets that 8 electrons is what bonding is all about, okay? So let me review bonding for you. We've done this a long time ago. So bonding, there's two kinds of bondings, ionic and covalent. And ionic bonding is from transfer of electrons. Ionic bonding is between metals and non-metals. We have cations and anions in ionic bonding. Ionic meaning ions, right? So you have ions in there. And generally these compounds have high melting points, okay? Now covalent compounds, on the other hand, they're a little bit different. They are formed from sharing of electrons. This is only between non-metals, so which means there are no ions, okay, in covalent bonding, and then their melting point is a little bit low. Now, if you don't remember the last part, it's okay. It'll come to you naturally later on, but the first three portions are really important over here, okay? So the transfer of electrons and the metals, non-metals, because when you look at any compound, remember when you started naming any compound, the first thing you do is you see if that compound has metals and non-metals or just non-metals. That's how you start naming also. And so the same thing you will have to do with bonding as well. Okay, you start to see if something is bonding between metal and non-metal, or is it just non-metals. That is how you will figure out if something is ionic bonding or covalent bonding. So as we start learning bonding, the first thing we have to learn about then is what's called the Lewis dot symbol, or the Lewis dot structure. Okay, and the Lewis dot structure is really all about showing electrons, and specifically the valence electrons, okay, that we have. Now remember what I said, there are a maximum of 8 valence electrons in any element, okay, because any extra electrons, they will actually go into the core shell, they will not go in the valence, okay. So any valence there, you only have 8 electrons in the valence shell, so which means you only have to show 8 electrons, okay, anywhere. So how do you show those electrons? So I have shown them to you over here. This is just a sample of some of the electrons. So for hydrogen, there is only 1 electron. Now the Lewis dot structure says that you should have only 1 dot, okay. Now, some people like to draw crosses also, and when I say some people, I mean me. So for example, you can have hydrogen, you can draw that as a dot, but you can also draw a cross, okay? Now, one of the thing about drawing these dots and crosses is where do you draw them, okay? And so I've given you an idea of where to draw these things. So you might remember from a long time ago, we started learning about mass numbers, atomic number, right? So let's say you have a symbol here. So we have these four corners, okay, that we have already occupied in any element. So this corner here was for the mass number. This is for the atomic number. This is where we put the charges, right? So -2, -3, +1. That's what we goes in the top right corner. And the bottom corner here on the right hand side, we put the proportion. So if you have something like CO2, well, that too goes down in the corner. So which means what is available to us? What's available to us is these spaces. Okay, so top, bottom, left and right, those spaces are available to us. So that's where you're going to write these dots. Okay, so that's what you will see here also, is what I've shown is these electron dots on the bottom or the top. Now again, you want to draw a cross, you can draw a dot, you can, both of them are acceptable by me, but dot symbol really means dot. Okay, but anyhow, so what you're trying to do is you're trying to show electrons. Now when you show these electron dot structures, I want you to keep one thing in mind, okay? And that was something that we did a while back, in which we were trying to fill electrons, okay, in box configuration. And we said that, you fill electrons singly first, okay? And then you start pairing them up. So I would like you to do that yourself here also, okay? So you can see carbon, you fill electrons singly first on each side, and then you start pairing up the electrons. Okay, so you can pair up wherever you want, it doesn't matter, top, bottom, left, right, that's up to you, but you need to try to do that. And again, if your foundation is good, then later on you will have a better time with structures. Okay, so it's not a good idea to draw carbon like this, with 4 electrons on one side. I mean, that looks kind of silly. Okay, so let's not do that. Distribute all the electrons around as symmetrically as possible. Okay, so that's your Lewis dot structure. Is very simple. So again, the maximum number of electrons you have to show is 8. Okay, then the Lewis structures for cations. The Lewis structure for cations means that you don't have any electrons, right? Because cations will like to give electrons. And remember, group 1 gives 1 electron, group 2 gives 2 electrons, group 3 gives 3 electrons. And then after that, they like to take electrons, right? So that's anions. So which means Lewis structures for cations, group 1, 2, and 3 is what we are talking about. So group 1, let's say you have sodium, okay, which has 1 electron. Once it gives its electrons away, 1 electron away, doesn't have any more electron left. So all you have to do is draw an A+. That's it. Okay, so I've shown here for aluminum also 3 electrons, all 3 of them given away. So which means all you have is the cation, and that's it. Okay, you don't have anything else in there, so no more dots. Okay, now you don't have to show square brackets or anything like that. And if you want to, I mean, you can, it's just generally like, no. Okay, so no square brackets, just leave it as it is, and that should be fine, okay, for drawing the cations. Lewis structure for the anions, on the other hand, is where the elements have accepted electrons. So once you accept electrons, so now you have more electrons. Okay, so again, remember, I've and I've written it here also for you. Group number 7 will accept 1 electron, 6 will accept 2, and then 5 will accept 3 electrons. Okay, and why is it doing that, by the way? And we'll talk about this more also, but now you understand group 7, which has 7 valence electrons, can accept 1. Why 1? Because 7 plus 8 is equal 7 plus 1 is equal to 8. Yeah, I gave the answer away. Okay, anyhow, so you want to have 8, right? That's the magic number. So that's how these elements will accept the electrons. So now when you accept electrons, then you have to show those electrons. Okay, when you gave electrons away in the previous slides, which was the cations, then you don't have any electrons. Okay, but when chlorine accepts 1 electron, then now it has an extra electron here to show. So it had 7 electrons to begin with, and now there is 1 more. Now, which 1 more is the 1 more? You don't know, I don't know, it doesn't matter. Okay, so long the count is 8. Why? Because an electron is an electron. Okay, that's it. So it doesn't matter where you put it. Okay, so it could be any electron. But anyway, now in this case, you have to show the square brackets, and now you have to also put the charge, and the charge goes outside the bracket, okay, not inside. Inside, just leave it for the electrons, okay. Why do we need the square brackets here? We need the square brackets because you have a full shell, okay. You have all these electrons over here, so you need to kind of contain them, okay. Just think of it that way, all right. And then draw the negative charge outside. So here is oxygen. Oxygen can accept 2 electrons, so once it does that, then you have a full shell, and then you show this 2 minus outside the square brackets. It's square brackets, not the curvy ones, not the parentheses, okay. So this is square brackets. Now you can draw dot structures like this, okay, but if you want to kind of behave like a chemist, then you can draw lines also, okay. Each of these lines that you see here, they indicate 2 electrons, okay. So chlorine, which has 7 electrons, so 2, 4, 6, and then 1, 7, okay. So that's how it goes. So each line indicates a pair of electrons. So when you have 8 electrons, all you have to draw is 4 lines, okay, outside. So it makes your structure a little bit neater and cleaner. There are some things that you cannot do. So for example, oxygen here, look how I've shown these 1 electron, these 2 electrons on one side and then on the other side. Here I can't do that, and that's okay. It doesn't matter, okay. So long you still have an equal distribution, it's going to be fine, all right. But this is a nice way also to write your electrons, okay. So if you want to draw your Lewis structures with lines, I'm fine with that too. So the first bond we want to learn about is ionic bonding, okay. And ionic bonding is about transfer of electrons, okay. And the transfer of electron is happening from the metals to the non-metals, which means metals will give electrons, non-metals accept electrons. Why do metals lose electrons? Now you know, is because they have low ionization energy, right? And non-metals actually have high electron affinity, so they like to accept electrons, okay. So it's a very nice system, all right, very easy to do, and really these reactions work very well. So you have a metal and a non-metal, okay. Now the thing is, how does it happen? And it doesn't take really a lot of energy. It does take some energy to do this, but the energy that is lost and the energy that is kind of, causing the stability of the final compound is so low, okay, which means they're very stable compounds, okay, in the end. So what happens? So here is calcium. Calcium has 2 electrons, and here is oxygen. Oxygen needs 2 electrons. So calcium gives the 2 of its electrons to oxygen, okay. And then here is your ionic bonding, all right. So here's calcium, and then here is oxygen. Now if you don't show the plus sign, that's totally fine, because right now we're just showing it because I want to show you that the both of the ions are present. There is no line between them, okay. So what I mean by that is that when you show your calcium and oxygen bond, you don't write it like this, okay. That's completely wrong. The Lewis structure for calcium is 2 plus, and the Lewis structure for oxygen is this, okay. So that is how you write your Lewis structure. There is no lines, there is no particular bond. This is what we call association, okay. And remember, we've done association dissociation reactions before. So the dissociation happens when, these two will kind of part ways, all right. So this is just an association, and so we don't show any lines, okay, for ionic bonding. So keep that in mind as you're learning ionic bonding. So just to go over, okay, how this works, because I know you have done this before, but we'll just go over this with some of the problems so you understand this, because the Lewis structure of ionic compounds is really very easy, okay, to do. So form the structures between these compounds, these elements over here. So the first one is sodium and chlorine. So the most important thing is for you to figure out what needs how many electrons, okay, and that's all. So if you remember back when we were doing our bonding also, okay, this is kind of what we did, not bonding, the nomenclature, this is what we did. Sodium is plus and Cl is minus, and then you do the crisscross, right? So all you have to do is do this, and once you know what the ratio is for Na and Cl, well, then you write the Lewis structure, okay, that's it. So the Lewis structure should show the Na plus and the Cl minus, show all the electrons, okay. the key thing about Lewis structures is showing all the valence electrons in there. So calcium and fluorine, and then here you can see that calcium gives 2 electrons and fluorine needs only 1, right? So which means that you will need 2 fluorines, okay, in order to take those 2 electrons that calcium has to give. Or you can do this and then figure out what the formula will be, and once you know the formula is CaF2, then you write the Lewis structure. Okay, CaF2 is not the Lewis structure, that is just the formula. Okay, that's not Lewis structure, this is Lewis structure. So anyhow, so I have done the aluminum and oxygen bonding in that crisscross manner. So once you figure out what is the ratio that you need, then you go ahead and do this. Now let me just show you one more thing here before I move on, and that is how you write these coefficients, okay, these subscripts. So if you have calcium fluoride which needs 2 fluorine, you need to write the 2 as a coefficient here, okay, in front of fluorine. So that's how you will write and indicate that there are 2 fluoride ions, okay. And so for aluminum oxide, where there's 2 aluminum and 3 oxygens, you need to write the 2 in front of aluminum and 3 in front of the oxide, okay, to show that the ratio is 2:3 for aluminum to oxygen. Okay, that's how you need to show it. That's just the rules. Okay, and I'm not doing anything here that is out of the ordinary. This is how we write for the Lewis structure for ionic compounds. Okay, so there is nothing much more to it. Keep it simple. Okay, and that's all we are going to cover as far as Lewis structures are concerned. So this is it. Covalent compounds are going to be our major concern here, because in covalent compounds we have to share electrons, and sharing electrons is a little bit deeper of a subject than just saying it shares electrons. Okay, so we need to figure out how many electrons are being shared and how are they being shared, where are the electrons, all those kinds of things. Okay. For ionic compounds, electrons are given, electrons are taken, transaction over, done. Okay, but with covalent compounds, with the sharing, you have to be a little bit more careful. All right, so here are some simple sharing going on. Okay, so hydrogen has 1 electron excuse me, and it's sharing an electron with another hydrogen, and so both of them need 1 more to become 2, which is the not the octet rule, but this is the duet rule, because hydrogen can have a maximum of only 2 electrons. So it's considered the duet rule, but we still call it octet, even though we know it's not 8 electrons. But anyhow, so both of them will need to share that 1 electron, so that when you look at just one hydrogen, you can see 2 electrons. When you look at the other hydrogen, you see 2 electrons on there. So which means at any given time, each of these hydrogens can claim to have those 2 electrons, okay, even though one of them is belonging to hydrogen, the other one belongs to the other hydrogen. Okay, so I've colored the electrons just to show you that each one is bringing its own electron, but honestly speaking, it doesn't really matter, because at the end, this is what the structure would look like. Now you will actually have a line between the 2 hydrogens, and that line indicates the sharing of the electrons. That line indicates 2 electrons. Okay, so remember that line that we drew first, that was 2 electrons, and now it's between 2 atoms, indicating that these 2 electrons are being shared between these 2 hydrogens. We can do the same thing for chlorine also. So chlorine has 7 electrons. Each of these chlorines is 7 electrons, which means that it needs to share 1 more electron in order to become 8. And that's what it does. So once it shares that 1 electron here, so now if I just cover this 1 chlorine on the right hand side, then you have 1, 2, 3, 4 pairs, which is 8 electrons on the left side. And then on the right side, the pink electrons, 1, 2, 3, and that 1, so that's 4 times 2 electrons. So that's 8 electrons at any given time then. Okay, and so each chlorine has 8 electrons now. So that's sharing of electrons. Okay, that's going on here. Now, if hydrogen and chlorine had to form a bond, hydrogen has 1 electron and chlorine needs 1 electron also. So both of them will share 1 electron each, and then you get something like this, which is HCl. Now hydrogen and chlorine are sharing 1 electron, and then there are electrons left over on the chlorine. And again, because we are drawing Lewis structures, you have to show all the electrons, okay? And again, don't worry about the pink and the blue and the black electrons. I'm just showing those to show you that which electrons are where, but honestly, an electron is an electron is an electron, okay? Now with covalent compounds, what's going to happen? Okay, so let me just tell you. With covalent compounds, I have to give you the structure, okay? Because you might remember from back when we were doing compounds is that you can have different kinds of compounds, right? So you can have something like CO or CO2. So which means if I ask you to form a compound between carbon and oxygen, you don't know which one to show. Do you show CO or do you show CO2? Okay, so I have to give you the compound. Okay, I have to say, okay, draw me the Lewis structure for this molecule. Ionic compounds you can do yourself because ionic compounds is a transaction and you know the charges and you can go and figure out the formula. Okay, but covalent compounds, it's a little bit more challenging. So I will give you the formula and all you have to do is you have to write the structure. So I'm going to tell you how to write the structure. Okay, once we have kind of finished talking about all the different kinds of bonds possible. Okay, so that's at least one good part, okay, about drawing Lewis structures for covalent compounds. Okay, so the different kinds of covalent bonds you can have, and this also gives you examples of different structures, okay, that you can have. So you can have a single bond. So a single bond was what we drew for chlorine, okay, so which means you have only one pair of electron being shared between chlorine and chlorine. Here we're going to see a double bond. A double bond is in which two pairs of electrons are being shared. So here if you look between carbon and oxygen, you have two pairs of electrons being shared. That is shown in this double bond and it's called a double bond. Okay, so you have a double bond on both sides, and on both sides you have 4 electrons here and 4 electrons here. And now you understand the triple bond. In triple bond you have 6 electrons, okay, that are being shared. So 3 pairs of electrons. So 1, 2, 3, and you see triple bond there. So the triple bond, double bond, and single bond, remember when we talk about these, this is only between two atoms. Okay, so if you have a structure that's more complicated, it can have a single bond and double and a triple bond also. Okay, that's a different thing. Okay, but I'm just classifying these bonds so that when I say there is a double bond between carbon and oxygen, you know this is what a double bond means. Okay, that you're sharing 4 electrons in there. Okay, so you have to draw a double line in there. It's a simple thing, but still it needs to be explained. Okay, then we need to also understand the types of electrons we have. Okay, so we have the types of bonds, which is the single bond, double bond, triple bond, and now we have different kinds of electrons. And the two types of electrons we have in any kind of a covalent structure is bonding electrons and non-bonding electrons. Okay, so I have shown you here, for example, in HCl, hydrogen chloride, the bonding electron as in the black one and the non-bonding are going to be the red ones. So the non-bonding electrons are not bonding with anything. Okay, they're just there. So they're also called lone pair of electrons, by the way. Okay, so lone meaning they are by themselves. So the lone pair meaning 2. So they have chlorine right now has 3 lone pairs of electron, or you can say it is 6 non-bonding electrons. Be careful of the language, okay? So when we say we have a lone pair, it means 2. When we say we have 2 lone electrons, it means we have 2 lone electrons, not 2 pairs. Okay, so mind the language. Be careful of how you're counting your electrons. So here in HCl, you can see that we have that 1 pair that is bonded and the 3 pairs that are non-bonding. In carbon dioxide, you can see the pairs that are bonding, which are the double bonds, and then the non-bonding electrons are on oxygen. There are no electrons left on carbon. So by the time you write the Lewis structure, you have to show all the electrons, right? Wherever they are. Once you show the electrons everywhere, then you will know where the electrons are left over. Are they left over on carbon? Are they left over on oxygen? Okay, so in case of carbon dioxide, carbon has 4 electrons and all 4 of them are bonded, okay, over here. So you can draw the structure if you want as a dot structure also. So if you see this, so you have carbon with 4 electrons and then you have oxygen with the two electrons that are bonded here, and then oxygen is here, and I'll just draw the lines here because that's not an issue. I want you to see the the bonding electrons. There are two pairs on both sides, okay, that are bonded between oxygen and carbon. And then the lines that I have drawn, those are the non-bonding electrons. And it's really important for you to know these, otherwise I wouldn't go through this. So later on, we are going to talk about what is the bonding and what is the non-bonding electrons, okay? So you need to understand that concept. So how do we write Lewis structures? Okay, there is a whole process for writing Lewis structures, and it can seem a little tedious, but then that's why I am here, right? To make your job a little bit easier, okay, and teach you how to do this in a very efficient manner, okay? So you're not stuck with going through process 1 through 7 every time you draw a Lewis structure. That's not how it's supposed to happen, okay? But I have given you the steps so that initially when you're drawing all of this, then you can go through all of these steps if you needed to, okay? And I'm not going to read all of these for you because this is not really the process that I follow for writing Lewis structures, okay? So this is really good when you're starting something, okay? So I'm going to teach you how to start. So in the next slide, I'm going to show you how to work all of this, okay? And then in the next one, I'm going to show you how to do this faster. And you will see it's not really that hard, but still this list is going to be there for you. Okay, so first write the Lewis structure, then count all the valence electrons, then you draw the skeleton of the structure, then you subtract. This is called electronic bookkeeping also, by the way. Okay, when you assign electrons, when you write all the electrons and you subtract electrons that you have already added to the structure. So that kind of electronic bookkeeping makes sure that you have taken account of all the electrons, because again in Lewis structures you have to account for all the electrons, okay? So then you figure out, you know, how many electrons are going to be bonding, any non-bonding electrons and whatnot, okay? At the end, add all the electrons to make sure you have the right number of electrons. So this slide here kind of goes through all those steps, okay? And then I've just skipped the 7th one because we are just counting all the electrons in there, okay? So here, if you're writing the structure for water, which is H and O, so here you will have 2 hydrogen atoms, okay? And not just 1 hydrogen, so I need to write 1 more hydrogen here. And I can do that right now also for us, at least for the video. There we go. So, and here this is going to be times 4, okay? This oxygen is times 2, and this oxygen is also times 2, okay? So you know that how many atoms you have because you're counting all the electrons, right? So you need to kind of know all those electrons in there. So you count all the electrons, okay? That's the second step. So once you've written all the atoms out, you count all the valence electrons. So you know how many total electrons you have to take care of. You put one atom in the middle, okay? And this is always going to be the biggest issue. What atom do I put in the middle? So in a diatomic, it doesn't matter, right? You can put, there's no middle. But when you have multiple atoms, what do you put in the middle? So generally you look at the periodic table, unless you've already memorized it, which is fantastic. So, but otherwise you look at the periodic table, and whatever element is on the left side of the periodic table, that goes in the middle. Whatever element has the highest valency, which means the charge, okay? So -3, -4, that goes in the middle. So oxygen is -2, goes in the middle. Carbon is minus or +4, goes in the middle, okay? So that's how it goes. So you put that in the middle, and then you assign one, at least a single bond to every other atom that you have in there. Now, the best thing to do when you're doing this step over here, and this is regardless of whether you take a shortcut or not, okay? This one we're taking the scenic route, okay, right now. But even in the shortcut, okay, when you do this kind of thing, I would like you to be as symmetrical as possible, okay? Symmetrical meaning when you're drawing your 4 hydrogens, put them on the 4 sides, top, down, bottom, you know, top, bottom, left, right, okay? So put them all around symmetrically, okay? Don't make a chicken feet out of it, okay? So don't draw, you know, like 4 hydrogens like this. It looks very awkward, okay? So let's try and draw structures in a nice symmetrical manner, all right? So put the highest valency atom in the middle. and then put the two other or whatever atoms you have, put them on the side. So in case of water and methane, it was hydrogens. Carbon dioxide is oxygens on the side. Okay, assign 1 bond each. Once you've assigned those bonds, then you subtract those electrons. So each of these bond is 2 electrons, so you subtract 4 electrons because that's a total of 4. So you have 4 electrons remaining then, okay, in there. So that's what this electronic bookkeeping row is all about, is making sure that you're keeping track of your electrons, okay, in there. Okay, the next step then here, oh, look at that, methane, it's all done, okay, because methane, you have actually taken account into all electrons. So there's no electron left over, which means actually the structure for methane is done, okay, that was quick, okay. All right, so now let's look at water over here. So we have 4 electrons left now. Where do those 4 electrons go? Now those 4 electrons will be either bonding or non-bonding. Okay, they can be either. So if you look at oxygen and hydrogen, you know that hydrogen does not have any more electrons on there. It cannot have more than 2 electrons. And so you've already fulfilled that for hydrogen, which means all those 4 electrons that are remaining will now go on oxygen. That's really what we are meaning by taking care of this, okay, by subtracting the electrons and trying to figure out how many are left over. So then you put in those electrons and your structure should be done, okay, at that point. Methane was done already, so now let's come on to carbon dioxide. So we have 12 electrons left for carbon dioxide. Okay, so in carbon dioxide, since you have 12 electrons left, you need to distribute those electrons. Okay, now remember, carbon is supposed to have 4 electrons, so you cannot give it any more electrons than it can handle. Okay, and remember, 4 pairs of electrons means you have octet. 4 pairs means 4 times 2, 8. Okay, at that point. So if you look at the structure that we have right now as an intermediate structure for carbon dioxide, look at carbon here. Carbon has 1, 2, so that's 2 times 2, 4, 5, 6 electrons. So that's not really a very good structure, okay? But right now we are just assigning electrons. That's all we are doing, okay? So we are distributing those 12 electrons. So we distribute those electrons over all of these atoms that we have remaining. So now since we have single electrons left over, if everything is paired up, by the way, that's a happy electron, okay? Electrons like to be paired up. So if you have any single electrons left, which is what is left here, when you look at carbon dioxide, okay, let me just tell you one more thing here real quick, okay? When you're looking at this structure here, this is what you do, okay, is you try to figure out how many electrons belong on carbon. So you have these 2 electrons right here, right? One from oxygen, one from carbon. One here from carbon, one here from oxygen. So which means that carbon actually has these 4 electrons. But when you're being asked in this structure how many valence electrons carbon has, then you're going to say that carbon actually has 6 valence electrons, and you're going to include the bonding electrons there too. So that's 2 and 2 and then the 2 in the middle. That's 6 electrons. So that's how you know that carbon is not happy yet. Okay, remember octet is the happy number. So carbon is not happy yet, okay, in there. So we need to kind of work on carbon a little bit to make sure that it has enough electrons, okay? So what we do at this point is we take those single electrons. So there's a single electron left here, single electron here, single electron here, and then you can use your arrow or not, or you can just use a pen and then say, okay, we're going to share 1 electron and we are going to share this 1 electron here, and then, or you know, on the both on the same sides, that's fine too. And then this electron and this electron are being shared here, and that's how you get the double bond. Okay, so the 2 pairs, the 2 electrons from here and then the 2 electrons from here. Why are we doing this? Again, because we want to make sure that no single electron is left. Okay, every electron should be paired. All right, as much as possible, you should try to do that. So now we have the new structure for carbon dioxide, and that is this one where everything is paired up, okay? And then you can count electrons again and everything will turn out to be fine, okay, in there. Okay, so I think I have something going on here. I'll have to check, but it should be a total of 16. So 2 times 6, 12. 12 plus 4, 16. So it should be 16 over here, okay? But anyhow, I'll correct that. Anyway, so the same thing you do for oxygen. Oxygen, you connected with 1 bond. So which means that you've taken care of 2 electrons. So you have 10 left over. You distribute the 10 electrons on the oxygen. And then those single electrons you will pair up and form the second bond, okay, over here. Once you have the second bond, and then oxygen is happy. How do you know it's happy? Well, you just cover one of the oxygens and then count all the electrons on the left side of the oxygen. Then you cover the left one and you count on the right side, okay? So just count all the pairs. So 1, 2, 3, 4 times 2, 8 electrons. So this is a stepwise method and you can do this, okay? It's a little bit long, but you can still do this to follow, writing good Lewis structures. And here's the quick way for writing Lewis structures. So this is what I do, okay? This is how I remember my stuff. And so my stuff is that, I remember that hydrogen and halogens will form single bonds, okay? Unless halogen is in the center. When halogen is in the center, like chlorine, bromine, if it's in the middle, then we've got issues, okay? But other than that, hydrogens and halogens will always have one bond if they're terminal, okay? Oxygen and sulfur can have only 2 bonds. Now, can they have more bonds? They can, but not in a neutral structure. Okay, in a neutral structure, you can have only 2 bonds, which means what? You can either have a double bond or you can have 2 single bonds. Okay, that's what we can do for oxygen and sulfur. Now, once you remember how many bonds every atom is supposed to have, then you are halfway there, okay, honestly, because this is what you can remember and write structures easily. Nitrogen and phosphorus will have 3 bonds, okay, which means that you can have either 3 single bonds, a double bond and a single, or a triple bond, okay? That's how it goes. And so, if you want to write this for yourself, you can. I didn't write it here, but like, hydrogen is going to have a single bond, like halogen is X, so you can have a single bond. Oxygen, so it can have a double bond, or oxygen can look like this also. Nitrogen, 3 bonds, or nitrogen can be triple bond, or nitrogen can have a 2 bond here and a double bond there and a single bond. Those are the variations you can have for nitrogen. So once you know that you have 3 bonds on nitrogen, you know it's a happy nitrogen. Why is it a happy nitrogen? Because nitrogen also has a pair of electrons that's going to be left over. Why? Because nitrogen is supposed to have 5 electrons in the valence shell. Why? Because it's in group number 5, right? So group number 5 has 5 electrons, okay? So where are my 5 electrons on nitrogen? My 5 electrons on nitrogen are 1, 2, 3, 4, 5. The other electrons that I'm showing with the bond, they are actually coming from another element, okay? So that's how it's going. So the 5 electrons are the blue ones, okay, that nitrogen has. And then the red ones here, those would be coming from another element. That's how it has the 8 electrons. I hope you see what I'm trying to show you, okay? So the same thing goes with the oxygen also, okay? In oxygen, I haven't drawn the lone pair of electrons, but there are the lone pairs. So again, if you have 1, 2, 3, 4. I shouldn't say that. I should say 1, 2, 3, 4, 5, 6. These belong to the oxygen, okay? And then you have these blue ones belonging to the other element. And that's why you can say oxygen has to have a double bond or 2 single bonds, okay, in order to be happy. So carbon then needs 4 bonds, okay? And this is one way of looking at things, okay? If you want to, the other way of looking at things is you look at the periodic table, okay, that you have. And in the periodic table, you will see that, here is your group number 8, okay? And then here is group number 7, here is group number 6, here is group number 5, okay? So 5, just that, there we go. So this needs 1 more electron to get there, right? To get to number 8. 6 electrons means that you need 2 more to get there. Group number 5, it means you need 3 more in order to get there. You see the 3 bonds? Okay, so that's another way of looking at how many bonds you need. Okay, once you remember that, everything is easier then, okay, for you. So here is the structure for ammonia, NH3. So when you're writing the structure for ammonia, you're going to start with nitrogen in the middle because this is of higher valency. So then as soon as you put nitrogen in the middle, you put the 3 hydrogens all around it symmetrically, and then don't forget to put the lone pair of electron on nitrogen because nitrogen is supposed to have 5 electrons, and right now you're only showing 3 electrons on nitrogen. Okay, so that pair makes it complete octet. Okay, so 1 2 3 4 times 2, that's 8 electrons. Okay, so nitrogen, 3 bonds, happy nitrogen. Okay, HCN, so here we have 3 atoms. In these 3 atoms, you will just write them like that, okay, which means that H, carbon goes in the middle and then nitrogen is on the other side. So you can start like this if you want, but then you know that nitrogen can have up to 3 bonds and carbon can have up to 4 bonds. So you draw a triple bond over here. So now everybody is happy, right? Hydrogen with 1 bond, carbon with 4 bonds, and nitrogen with 3 bonds. But nitrogen has electrons left over. Don't forget that. Carbon has no more electrons because carbon had 4 and all 4 of them are bonded. Hydrogen had 1. That's all bonded. Okay, so keep it simple and work on your structures. You have study sheets, so many study sheets in your in your package. Just work on those, okay, and you will see that it gets easier and easier. We also have exceptions to octet rule though. Okay, so we have the octet rule which makes everything happy and 8, but we have 3 exceptions. We have incomplete octet, we have an expanded octet. Expanded is not octet anymore, but we have more than 8. And then there's an odd number of electrons. So here I was just emphasizing to you that you have to have paired electrons, but now I'm saying, but there's an exception, okay? Exceptions are always harder to remember, okay? I've said that before, but you have to remember it, So, and you have to remember also which elements are the ones that are going to have those exceptions, okay? So let's go through each of them. So the first one here I want to take is the incomplete octet. Okay, and the example there is of boron trifluoride BF3. So boron is, okay, here I have hydrogen. So let's go ahead and change this one to boron hydride. Okay, so we'll change this one here to H as well. Okay, but anyhow, that's a small point. The structure doesn't change. Okay, that is still the same because the main thing we are looking at is actually the central atom. Okay, in here, the central atom is going to be boron. And so boron has 3 electrons, hydrogen has 3 electrons, so 1 electron each. That's why the 3 times 1. So we have only 6 valence electrons, okay? So boron goes in the middle and then you have the 3 hydrogens. Boron does not have any electrons left over because it had 3 and all 3 of them are bonded. So there's no electrons left over. And what that means then is that boron doesn't have an octet. Okay, and that is how it is. Where is boron? Boron is in group number 3. Group number 3 has 3 valence electrons. So at any given time when you're bonding 3 electrons, you can only bond 3 electrons. So how many can you bond with that? Only 3 more electrons, which gives a total of 6 electrons, and that's it. Okay, and that's why boron will always have an incomplete octet. Okay, aluminum is the same way. After that, going down the group, it becomes into metals, so that's a different kind of bonding. Okay, all right, now I'm going to do the odd number because the expanded shell takes a little bit more space, so it's on the next slide. Okay, but we'll just do the odd number first because odd number is very specific to nitrogens. Okay, it's not that other cannot have it, they can. Anything any element, okay, usually any element that has odd number of electrons already on the valence shell, like group number 5, group number 7, they will have odd number of electrons. So maybe some of them are not paired, okay, at a given time. So here is an example for NO, which is nitrogen monoxide. And so you have 5 and 6 electrons, 5 coming from nitrogen, and oxygen has 6 electrons, so you have 11. But by the time you write the Lewis structure like this and you assign all the electrons, oxygen will have 2 pairs of electrons and then the double bond. Oxygen is happy, okay, this oxygen is not a problem over here. Nitrogen is the problem, okay, because nitrogen, there's 1 electron that's left which is not paired. So how many electrons nitrogen has right now? 1, 2, 3, 4, 5, 6, 7. So it's short also 1 electron, but it is also got an unpaired electron, okay, in there. So some elements, that have, as I said, odd electrons like group 5 and 7, they're going to have this kind of an exception, okay? And if you're wondering, well, do these compounds exist? They do exist. They're a little bit more reactive than others because, everything should be paired and everything should be an octet in order for them to be stable. So yeah, these are not very stable compounds. For the expanded shell now, expanded means you have more than 8 electrons, okay, in there. So first of all, we need to understand is how can anything have more than 8 electrons? Because technically speaking, as I said, in the valence shell, you can only have 8 electrons. After you fill that 8 electrons, you get to the group 8, then here's my hypothetical periodic table, okay? So here's the 8 electrons, then you go to the next shell, right, to start filling. So are we adding more shells? But that's not what happens, okay? So for expanded shells, you have to look only for the elements that are in the third period or below. So which means you're not looking at row number 1, which ends with helium. You're not looking at row number 2, which ends with neon. You're going to start looking at row number 3, which ends in argon, okay? So silicon, phosphorus, sulfur, chlorine, these elements, and any of the elements below that, okay? Arsenic, selenium, bromine, iodine, any of those elements are capable of having an expanded shell. How? Why? Okay, why can they have an expanded shell? And that's because of the d orbitals. Remember, in the third shell, you start having d orbital. You just don't fill them until you fill the 4s, then you fill the 3d electrons, then you go into the core to fill the 3d. So which means you have those d orbitals there, they're just empty. It's like having a big mansion and then you have like 4 bedrooms or 5 bedrooms empty and you're living in only 3 bedrooms, let's say, so you have space, okay? So that's where the electrons will go then, all right, in the expanded. So shell number 1 and shell number 2 do not have d orbitals, so they cannot have an expanded shell, okay? Only elements below that or starting from shell number 3 can have the expanded shell. So here are some examples, okay, for the expanded shell. Phosphorus, for example, PF5. So phosphorus has 5 electrons, okay, and all those 5 electrons can bond with fluorine or chlorine or anything like that, okay, it's possible. So at this time then phosphorus has 10 valence electrons, 1, 2, 3, 4, 5. Sulfur has 6 electrons and all 6 of them can be bonded. And that's giving you SF6 then, which means that those 6 pairs, that's 12 electrons. Okay, I mean, that's a lot of electrons. Okay, it's a lot of electrons for any single element. And we're talking going from 8 to 12. So that's like 4 extra electrons. And where are those going? They're going in the d orbital. Okay, so this happens. And these compounds are actually quite stable, okay, because d orbitals, it's fine. So long there is a space for them, it's okay, all right? So expanded shells are, quite stable. But then again, remember, okay, this is only for certain elements. It's not going to be for row number 1 and 2. Does phosphorus always form PF5 or can it form PF3 also? Because remember, phosphorus in group number 3, group number 5. So if nitrogen can form 3 bonds, can phosphorus also form 3 bonds? And yes, it can. Okay, so phosphorus is capable of having either 3 bonds or 5 bonds. Nitrogen can have only 3 bonds. Okay, similarly, sulfur, it's below oxygen. So oxygen can form 2 bonds only, remember? But sulfur can now form 2 bonds or 4 bonds or 6 bonds, okay, depending on what it is bonding with. So it has more choices. Okay, the last thing to talk about here, yeah, we're almost getting to the end of this little presentation. So it's covalent bonding, is it equal sharing? Now, technically speaking, when we share, we should be sharing equally, all right? But things sometimes don't quite work out, okay? And so in those cases, there is unequal sharing. If one element is more greedy than another, then there is unequal sharing, okay? When there is equal sharing, the electrons are equally shared, no problem, okay? Now, when you have an ionic bond meaning that you have plus and minus. Remember, there is no sharing going on, okay? So that's cations and anions. So that's a whole different thing, okay? When there is a covalent bond, there could be equal sharing going on. But when there is something called a polar covalent bond, that happens when there is an unequal sharing going on, which means that at this point, one element is pulling more electrons, it's a little bit more greedy. Well, I wouldn't say greedy. Greedy is a bad term, you know. I mean, it's just pulling more electrons. It's just its nature. It pulls more electrons, okay? And that nature is actually called electronegativity. It can't help it. That's what it does, okay? And so at that point, you get what's called a polar covalent bond, which you can see right here, as I've shown with these symbols, little delta over there, and that delta symbol, this delta, so delta plus, and then you can have a delta minus. Delta plus means they have a little bit of positive, and delta minus, you have a little bit of negative, just like you might be delta tired right now, okay, of listening to me, but still, okay, a little bit more and then we will finish, okay? But anyhow, so delta positive, delta negative means you just a little bit, okay, of charge on there, and that happens because electrons are unequally shared, all right? So here we are not talking about ionic bond. I just wanted to tell you that ionic bonds inherently are going to have cations and anions, okay? But this one is not cation and anion. This is just a charge distribution, okay? A little bit of distribution, unequal sharing, okay, sort of. And that comes from electronegativity, and that electronegativity is actually a property that elements have. There's nothing you can do about it. You can't change it. You can just learn it, okay? So electronegativity is the ability of an atom in a molecule to attract bonding electrons towards itself. So it's only occurring in a bond, in a covalent bond, it happens, okay? So one of the atoms is pulling electrons towards itself in a covalent bond. Which atom will pull electrons? So here is the trend, okay, for that. So we've done a lot of trends before, and here is another trend to remember now. So electronegativity increases as you go to the right, decreases as you go down. Now, electronegativity of metals is not going to matter, okay, as I said, because for metals, they just give and take electrons. They don't really care, okay, give electrons really. So this is mainly for the non-metals. The only non-metal on the left side is actually hydrogen, okay. These numbers is a little bit of a measure of their electronegativity. And these numbers you can use to calculate to figure out if a bond is going to be polar or not. Okay, how do you do this? Is you take these two numbers and you subtract them. So for, let's say, carbon, 2.5 minus 2.1 of hydrogen. So you subtract those two numbers and you get 0.4. So a polar bond will be anything that is 0.5 or above. So a CH bond actually is not polar, because when you subtract the two numbers, your number is 0.4, which is less than 0.5, okay? The most electronegative element on the periodic table is fluorine. So this one you will never forget, okay? Fluorine is the most electronegative, then oxygen, and then nitrogen. These three elements, they kind of stand out, okay? NOF or FON, whatever you want to call them. So they stand out with their electronegativity. Chlorine is another one that is a little bit more electronegative, okay? Bromine is a little bit less because electronegativity decreases as you go down. Sulfur, not electronegative. None of these elements are that electronegative. Okay, it's really these four elements that you have to kind of think about. By the way, as soon as you have two different elements, you have some sort of charge distribution. Whether it is, small or large, that's a different thing, but there is just a slight distribution, okay, of charge. Okay, so this is how we show the charge distribution. Okay, so I already talked to you about the 0.5. And then here, this is how you show that there is a delta positive on hydrogen and delta negative on fluorine, because fluorine is attracting electrons towards itself. Okay. Now, this is what we do to show that there is electrons being pulled. So this is something that you can draw as well, okay? And this is to show a little bit of polarity, okay, that's going on in the molecule. So this is the arrow, and then you draw a crosshair on that. So that shows polarity of the molecule. You draw it towards the negative charge, okay? That's how you indicate polarity. Okay, so here is, I guess, a solved problem with determining polarity. So you can go over this. I don't have to, because it's not that difficult. And also, it's been quite a while now for me talking. You must be exhausted. So anyhow, so looking at all of these, you look at the numbers of the electronegativity, you subtract them. And then once you look at the numbers, you can figure out which bond is more polar than another one, okay? Here, this one is an interesting one. So let me just talk a little bit about this. Okay, so using electronegativity, identify the polar bonds and then show the arrow on the bond to show polarity. So one of the ways that we also show polarity in a bond is by showing an arrow like this, that's shown in here. So for example, in the HF bond, you can show polarity like this also. Okay, so that's kind of what I have shown to you in this problem. So here, this actually should be going on this side. This is opposite. So nitrogen should be pulling electrons towards itself, and then nitrogen is pulling electrons over here, and then oxygen is pulling electrons towards its side. Okay, so that's kind of how you would show which element is pulling more electrons, okay, in a polar bond. So that is the indication of polar bond, and that's all we are doing right now with polarity, okay, in there. So again here, same thing, okay, so go through all of this to see if something is polar or non-polar. And I think that should be it for us, okay? Go through everything that we have done so far. I know it was a lot, but it is not that difficult also, okay? I think I tried to keep it simple for you all.